Bayesian long-term short memory model for crane stability prediction and uncertainty quantification in safety monitoring systems. Introduction and major changes. Mobile boom crates are essential in civil engineering. Their operational stability must be ensured under all load and environmental conditions to prevent from tripping. Recent advancements in AI have introduced recurrent neural networks and their variants, long short-term memory for crane stability assignment, due to their ability to model sequential time data series. However, those models are deterministic, producing single-point estimates without reflecting uncertainty. This limits their reliability in unexpected scenarios, where deterministic predictions may be misleading. Aim and research tasks. The goal of the research is to develop Bayesian OSTM model for forecast crane stability and quantify its own uncertainty. Together, those components will allow crane safety monitoring system to trigger an alert if the probability of failure exceeds critical threshold. Research methodology. Bayesian OSTM extend the standard OSTM architecture by treating all model parameters as random variables, allowing the network to capture and quantify its predictive uncertainty. We assume the standard Gaussian prior treating weights W as random variables. The training objective is to minimize the negative elbow, which is defined by a loss function loss. The mathematical model of stability index for the monorail crane. A binary threshold function for stability index S of a monorail crane is in the first operating position, when the boom is aligned along with the rail's track and the crane is under the load. Alert notification model for crane stability monitoring. An alert notification is triggered if the calculated probability of failure exceeds the maximal acceptable risk level alpha. The acceptance risk level alpha is determined by the confidence level used in the simulations, according to alpha equals 1 confidence. For example, when the confidence is 95%, the alpha is 0.05%. Architecture of Bayesian OSTM model for predicting crane stability. We propose model architecture consists of Bayesian LSTM layer with 32 hidden units, followed by a dense layer with ReLU activation. The final layer is a single neuron linear layer with no activation function, which acts as a linear head. The Bayesian properties of the model achieved through the application of Monte Carlo dropout. Dropout layers with a rate of 0.3 are applied after the recurrent layer and the dense layer. During inference, the dropout is kept active, and we perform multiple stochastic forward passes for each input data point. Experiment preparation. The model was developed and trained using the Python programming language in the following software equipment environment: PyTorch, NumPy, Pandas, Scikit-learn, and Matplotlib. Metrics to evaluate Bayesian LSTM. Coverage level is evaluated based on the loss function. Results. Figure shows that Bayesian LSTM training loss steadily decreases from 0.5 to 0.02, while validation loss initially drops from 0.2 to 0.066, then rises to 0.09, indicating overfitting. The support using early stopping preserve peak generalization by halting training when validation loss stops improving. Figure shows that alert simulation results which match the total number of alerts triggered by the model at the different confidence levels. As the required confidence level increases from 80 to 95%, the safety alert rises steadily from 60 to 101, indicating a consistent increase in the flagged edge cases. A sharp spike occurs at 97.5%, which alert jumping from 2 160, nearly 60% increase, highlighting the system heightened sensitivity and operational risk in this threshold. Conclusion. The research purpose of Bayesian LSTM model is to forecast current stability and quantify uncertainty, enabling safety alerts for the probability of failure exceeds a critical threshold. The model effectively captures the complex crane dynamics, achieving 0.97 accuracy with low training 0.2, and validation 0.07 losses. It shows the high confidence uncertainty 0.01 in predictable scenarios and flags high uncertainty cases linked to the potential risks. Thank you very much for your attention.